Okay. Welcome, everyone. This is our first joint edition between FAIMI and FAIMI, and we are very happy to have you all here. I think it's going to be an excellent afternoon. We are going to have very interesting talks and keynotes, and also it's very interesting to see from both point of views, more from an analytical point of view and from a fairness point of view. So I think it's going to be a fantastic joint workshop. Just as a housekeeping, we need to use only this PC, so I think everyone has sent me the presentations. If not, please do it now because we'll need to put it here. Also, the posters are not allocated, so we have a section, but you can put your poster wherever you feel. The numbers doesn't mean that you are allocated to a certain number. Also, whenever you receive questions, please repeat it because they're only an audience, otherwise won't be able to hear it. So if they ask something, just repeat the question and then you reply, please.
No, I'm just would like to say that this is the first year that many of these workshops have been merged, and I'm really happy that our two have, as Esther put it so eloquently. It's a really nice thing to see the pairing between the more empirical approach that's been taken by FAIMI in order to look at an incredibly important ethical issue in medical imaging, that of fairness. And I think it pairs really well with some of the more philosophical or theoretical approaches that we've traditionally taken at FAIMI. I couldn't be happier.
Then for FAIMI, we will run also some awards, and it will be great if you can help us by voting. So here's the QR code. If you can take a picture, we will put it also at the end of the poster teaser, but just for you to keep it in mind. And we also wanted to take this opportunity to present our online event. So it's going to be a free online event on the 6th of October, where we are going to have excellent keynote speakers, and also we are going to have some other orals from people from MICCAI and also as well from here in this workshop. So we hope that you can all join us. And if you want to register, the QR code is here as well as on our website. So you can go and just register. I think it's going to be also a really good online event. So I think with that, we are going to open in the session. The first one is 3 oral sessions. So thanks.
Hello, everyone. So just as a reminder also, maybe from that we will have the power pitches at the end of the first session, right? And so, well, then we will tell you how to organize that. Great. So we are really happy today to have Judy Gichoya with us as our keynote. So Judy is there. Judy, you wanna share your present? You have to stop sharing. But while there we are. So Judy is an assistant professor at Emory University in interventional radiology and informatics. Her career focus is on validating machine learning models for health in real clinical settings, exploring explainability, fairness, and a specific focus on how algorithms fail. And today she will be talking about shortcuts. So Judy, thank you very much for accepting our invitation, and the floor is yours.
Thank you again for the invitation. And again, I apologize. I would have loved to be in person, but it just turned out that I couldn't. And so, I hope that this is going to give you many questions at the end, and which is really my desire. I chose this topic of shortcuts because I think it's pretty interesting, and it's really something that I'm thinking about every day. And it matches 2 areas of my work. And I'm going to walk you through this phase to convince you that this is an area that deserves your attention to think about when it comes to thinking about bias, and why this is also a really difficult area to work on. Here are my disclosures, and nothing is going to be trying to sell you anything or bias you with this talk. And so getting on to business. If you've heard me speak, then you know that I've said that a picture is worth more than 1,000 words. And increasingly, I am convinced about this. And this presents the biggest power for us to either harness AI in ways that it's not possible today when it comes to deploying AI in the healthcare system, or can also be the supercharge for bias. And so this, this tension is something that we have to think about. And so to make my case today, I'm going to be describing some use cases of AI where it's only image-only tasks and why that is important, and then move on to the shortcuts and then try and combine this with a perspective on equity and bias. So last year, we published this paper which showed AI deep learning methods can tell you the self-reported risks of patients on medical imaging. There has been subsequent papers. I'm not going to spend my time trying to say, is this possible or not? I'm just going to use this as a launch form to tell you why I think it's important to think about these image-only models. Now, depending on when you were born in the US, now in Europe, some places you don't even record the racial and ethnicity groups, and the year of the census, you'd be called different things. And the reason why I show this infographic here is to show you that this is really not a biologic, condition. And this is one of the first areas of thinking about shortcuts. Are they biologic, non-biologic? Do they matter? For example, age is important for some chronic diseases or diseases that are found more in younger patients or older patients. But when models rely on these biologic and non-biologic conditions, for example, insurance, what do we do with them and how does that affect your model performance? So we had a variety of data sets, chest x-rays, chest CTs, digital hand radiographs, breast mammograms, cervical spine radiographs with different composition of the racial groupings and splits. There wasn't really much massaging here to try and fine-tune the model. After the second or third epoch, we really got good performance. And, we ended up showing that the internal validation is actually pretty good with AUCs on chest x-rays above 0.96. Now, I do want to just acknowledge that there are many subsequent works that have said, hey, here's the solution. But fundamentally, I think all of us will agree on one thing, that deep learning models are able to pick up social demographic variables of patients, whether we provide them explicitly or not. And if you can agree with that first premise, then you can understand why I'm discussing this way in terms of shortcuts. And so, I know that there's quite a lot of debate and, several experiments, but I think we can all agree that some form of social demographic variables are picked up by deep learning models. For our case, we did do a couple of experiments trying to figure out the confounders. And, I will, so far I've used shortcuts, I've used confounders. Later on, you'll hear association bias. The thing that is difficult to study about shortcuts is there's no one taxonomy or nomenclature that allows us to even consolidate what this is. And in our case, when we were thinking about what could the model be failing on, is it breast density that we know changes actually with different racial groups? Is it disease distribution? Maybe the Black patients were sicker. Is it some of the image properties? Is it the age? Is it sex? And unfortunately, after multiple experiments, we could never figure out that this is what is causing. There has been subsequent work that is saying it's maybe the sex grouping, but those works also confound in terms of the distribution of how many percentage of males and females from every group that they include. And that we know that deep learning models are actually pretty good at telling you if this is male or female. And so we feel that that's what the model is relying on. And so after multiple experiments, it's this concept that we not only show that the model performs well on just the image itself, but this modified image, this is after applying a high-pass filter. The AUC is 0.86 for the worst performing class, which is the white patient. And it still can tell you this is a Black patient or a white patient. So this is really bizarre. And it catapults at me to start to think and frequently refer to these hidden signals, because this, as a radiologist, even here, I cannot tell you that this is a Black or a white patient. And on this other end, now you have this sort of altered images, whether you add noise, you add, you make them blurry, you make them different pixel levels. And this is where the challenge comes in. And so This is some related work where we looked at just cardiac, vascular disease markers. Could you predict them from chest X-rays? Now, if you're trying to get a complication, yes, you can maybe say this patient is on dialysis, so they probably could be diabetic. But we find actually that the model does well to tell you that there's congestive heart failure, atrial fibrillation. Now, there is new work that just got published about these arrhythmias on chest X-rays. These are not patients who have cardiac valves, which would be telling you, oh, this has been fixed. This is just a bad rhythm of the heart. This is a morbidly obese patient. They have COPD. Some others have vascular disease and diabetes. And what was interesting about this work is we started to link it with the social deprivation index. And this is a zip code level, granular level marking of a mark of poverty. It tracks, the level of unemployment, lack of car ownership, average income, crime rate, high school dropouts, renting, and just tries to say, do you live in a deprived area? And if you have a high number, then you live in a deprived area, as you can see, mainly in the southern parts of the US. And if you live in a lower number, then you live in a better area. And what we see is that in this population, the non-white patients were living in more deprived areas compared to the white patients. And I'll show you how we tied those things together. This was the AUC values for the prediction of the 6 conditions. I think the worst performing one was around 0.76. And and then we started to say, okay, here's a chest X-ray, tell us about this patient. And this one, why I put language here is because the electronic medical record is never complete for patients who don't speak English as their primary language, because especially if you have to translate, people try to, I have been in this situation, the translation machine robot is terrible. And unless you speak that language, you most likely focus on what the patient is complaining about. And some of the records are not just as complete as they could be. And so absence of a code is actually a form of disparity. And in this patient, we were able to show that, yes, they had non-compliant diabetes when we went back to the chart, and they had an echocardiogram, which is a picture of the heart, ordered in the past for evaluation, but they just never were able to get it done. And so we were starting to see, well, the model is saying that there is a code for congestive heart failure. This is recent work that we published. Again, and what I say is that you should take this type of work. If we're going to move away from research to real world implementation, you should take this type of work and say, wow, how can this be, and then start to poke holes at it, because this, again, I started off by showing you this tension between these image only models and, and their performance. So you can imagine this is a type of work that you don't need to label with humans, right? So you just need your A1C values and the other diabetic markers. And now you can supercharge whatever you can do with this type of models. Tremendous impact on public health, obviously. And so we developed this model from around 270,000 chest X-rays from 160,000 patients. And this was validated on a prospective data set of around 10,000. And we had an ROC AUC value of 0.84 when there was a 16% prevalence of diabetes in the population. And the model, flagged around 1,000 cases as suspicious. And then when we took it to the external validation institution was at Emory, the performance was 0.77. And 5 of these patients, from when they had their chest X-rays, were subsequently diagnosed with type 2 diabetes. And what was interesting and what was well received actually was trying to move the needle for where could the model be looking at. And it's mainly was just looking at adiposity, which is fat measures. And as we know, this can be very troublesome, in medical imaging, and we were mainly looking at the clavicles. We used several approaches and the subxiphoid area. These two seem to be where the model was concentrating on. This is work from UCSF that has shown, from chest X-rays, you can predict the healthcare expenses of patients on, using deep learning. Now, their model, T is a model. If I say that as someone who works in fairness, you would be like, you should not be doing something like this. And the model here uses income, uses zip code level to try patient sex and age. Those totally would be biased variables. You can't, yes, if you're older, you're probably spending more just based on some of those things and the zip code income. But what is surprising is that the X and these are TX are the combination of the image-only models. You see that they start to perform well. How would just the chest X-ray model be able to, almost behave like it knew the zip code level, the income level, again, showing that these models are able to either pick up systemic, racism things that are in our data sets, or just some new factors that are not very obvious to the radiologist, and again, bringing that tension of fairness versus bias. So their example is another takeaway for why doing work in this area is extremely difficult. And you can see this is a chest X-ray that ended up having lower cost, and this is high cost. From a radiologist point of view, this is a young patient. This is a patient who is interacting with the healthcare system much more often because they have a chest spot. And these are the incorrect predictions. This to me is multifocal pneumonia, and ended up being labeled that it would be high, but this ended up being low. And this was labeled to be low, but ended up being high. But I can tell you that this patient is older based on their shoulders. They have calcium in their aorta, and their aorta is ectatic. So this is an older patient. So, trying to get proxies. But you can see that there's no real systematic way of telling you, okay, this is why this model doesn't work. I'm going to show you one last example in this sort of sequence of trying to show you AI deep learning models, yes, have ability to pick up many signals, some of them biologic, some of them non-biologic. And it's this area of this, people call them biologic age. I think we should start to call them image-based age systems. This is not different in radiology. We use it for bone age, one of the earliest deep learning applications for radiology, and also the brain age in Alzheimer's. And so this work looked at, could we use a deep learning model to generate a chest X-ray age and use that as an outcome for cardiac, cardiovascular disease. And what they found is where the chest X-ray age was older than the chronologic age, this is your actual age subtracted from your date of birth, those patients were dead at the time of follow-up, versus the ones where the chronologic age was, older than the chest X-ray. So the chest X-ray age was saying you're younger. And this is new work that's come up from Japan, where they looked at, chronologic age. But then what they did is that they looked at data from 5 different hospitals, but they looked at, what if I picked up an age from what's a normal patient without any disease? And you can imagine, yes, we don't really image and expose patients generally to radiation, but for their system, I think as part of an annual physical, you are getting a chest X-ray, at least in one of their hospital systems. And then they use that to say, okay, tell me the odds, the chance of getting disease, for someone else. And you can see in this picture, they just show where the hot areas are really where the model is focusing as you move from every 20 years time period. It's not unusual for us to think that the model is looking around the mediastinum, where we would start to see calcification or some meiotic disease associated with aging. And this is the odds ratio of different diseases. Some, are definitely in the lungs, so those are not surprising. But for example, liver cirrhosis here is pretty high, and unless you have decompensated cirrhosis, you shouldn't really be able to tell who has a high chance of that. Again, showing this amazing ability for these models to pick up things, although we don't really understand why. And so, I like to summarize this first portion of my talk to say, from my chest X-ray, you may not say my name, but you could say I'm Black, I am female, my chest X-ray age is 78, you can calculate my chronologic age, which means I'm aging faster than my age. I live in a deprived area. I have COPD and congestive heart failure, and I'm going to spend $15,000 in the next 2 years or 3 years or 5 years. And yet, as of today, we cannot really tell, is this real or it's not real? And it matters because as we move on to these image-only models, I'm going to show you 3 examples. One, it's October. So if you have a mom, you're married, you have daughters, make sure if they're eligible, they're getting their mammograms. This is when it's a breast cancer, a month. And Nancy, who unfortunately has passed on, was very faithful to getting annual mammograms. And you know that sometimes when you have dense breasts, these are very difficult to tell what's breast cancer in them. And unfortunately, after her breast annual screening, read as normal. 6 weeks later, she found that she had a lump. And when she went back to the doctor, the mammogram was normal, but because it was a diagnostic mammogram, she was found to have stage 3C breast cancer, very devastated, changed a ton of, did a lot of activism to change, the breast density notification and what should be offered, and including when you do those things, the insurance covers for it. The reason why I'm showing you this is that now we're starting to see these image-only models that tell you your breast cancer risk. So this is a disease where treatment has advanced much better, but we still don't know to understand the risk. It's even worse for minorities, Black and Hispanic patients who tend to die younger with more invasive disease and more aggressive disease at the time of diagnosis. But I know that I've put some bounding boxes here. This is not how this model works. It just tells you here is the risk of breast cancer. And what I want to show is that these are the 4 clinical tools that today people use to tell you the risk of breast cancer. And the MICCAI model, yes, if you have imaging, yes, that's sufficient. It encodes the data from the 4 images and then aggregates that value. And if you have the clinical information, well and good, we're going to use it, else we will still just have an arm that can just use the image only alone. And you see, for example, to tell you the breast cancer risk, the MICCAI model starts to perform better than the clinical models, that already this is their normal performance, so the minority groups are even lower, and it performs even better for Black patients. But is it because the underlying essence, if you remember my example of showing you chest x-rays can encode this type of data, really many imaging modalities, is it because it learns who are the Black patients and then gives them a better risk? We don't know, and this is why we have to think about how to mitigate shortcuts. A positive example, I think potentially positive, is we usually use this Kellgren-Lawrence score to tell you the degree of osteoarthritis. And what we see here is that you can get an algorithmic prediction score. This was built using patients' pain scores. It wasn't using, this was validated only on white male patients. And what Emma and Ziad showed is that it actually reduces the pain disparities when you control for race, income, and education. It's a fantastic paper. And that it improves who's eligible for treatment. So again, if I show you the charts here that show, can you predict race from the NIH dataset that they used? Yes, with 0.98. So are you narrowing the gaps because the model is learning from a different shortcut? Or are you narrowing the gap because truly, if we listen to patient information, you bypass even the very expensive radiologist annotations and inconsistent, then we can actually narrow some of these gaps that we know. I don't know the answer, but that's why we're having this. The last example is one that is actually just showing the power of image-only models. This group, what they do is that they train 2 models. One uses text and the pulmonary function tests, and then this other one uses chest x-rays, and then tries to use, predict my pulmonary function test and also predict the severity of disease. And what they show really is that the image-only model performs better. It performs better for different metrics compared to just the text only. Does the radiologist say this? And also that it actually performs better to tell you the severity. And when it makes a mistake, it doesn't tell you, it just is one level lower. And if there's not much of a difference in terms of treatment, of course, if you're normal, you don't want to be classified otherwise, but you see that you have better performance when you look at the image-only model. And so I went through showing you the evidence, at least, that we can all agree that there is some social demographic features that are encoded in images that these models are able to pick up. We don't know some why the model is able to do that. Some are biologic, some are non-biologic. And why it matters is as we move to these image-only models that are showing actually superior performance more than any other types of models, and especially in the area of health equity, where we see narrowed gaps. I think we need to almost tie those 2 fields together. And that's really my what happened after working on that reading race work. And so I told you shortcuts, confounders, association bias, and now this is clever hands. So this is a history a talk a little bit. This was a horse actually in the early 20th century in Germany, and it was famous because it had an apparent ability to perform arithmetic, recognize colors, and answer questions by tapping its hoof. But then, after a series of control experiments, it was found that the horse was actually responding to unintentional cues from the trainer and the audience. For example, if they knew that the answer is going to be correct, and start to associate that, or the voice tone, and then tap, and then sounds to be correct. And so we have clever hands. Actually, there's a paper published on this for brain MRI, is another term again for this world of shortcuts. And so hopefully some of you have seen this, where you give you say caption this image, and it's green hillside is described as grazing sheep because it's trying. Models are lazy. I think we all know that. And they use the lowest shortcut that they can use to do that. And when you add some noise, even if this is not recognizable, it has hallucinates. And then this work by John Zek, which showed pneumonia was mainly because of the radiographic markers. And this work is just showing if you change some of the text, it changes the answer if irrelevant. This is pretty common now in the era of large language models. And so this, the same paper, what they tried to do was come up with a taxonomy of shortcuts. And here they were just trying to show you an experiment of like labels and positioning, so the model doesn't learn stars or, moon shapes. It just learns where the position is and then predicts that. And, the reason why I show this is just for one takeaway, that most of the work, when we've come up with shortcuts and shortcut evaluation, it's rarely been because there's out of distribution drop or model performance drop, and that's when people start to investigate, and they're like, oh, it's because it's doing this. Most of the work hasn't looked at pre-hoc evaluation of shortcuts and how that affects model performance. And this is the same example that they show again in the sort of this concept of in distribution and out of distribution, and showing some of the things, for example, texture, it's sort of like you don't have to get a high ability, but it just looks at some of the features that are common and then decides that this is the class. And so really to look at some of these things in imaging, I think one of the best papers is this one, following John Zek's paper. And this is showing AI failure for COVID diagnosis because of shortcuts. As you know, in the first wave of COVID, we never had really normal chest x-rays. And so people started to use older chest x-rays. So this is the NIH data set. And obviously, this is from what people were publishing and picking those as positive images. And they created another data set. This is more real, based on PCR tests. And they did two interesting things. One, they first trained two models, and then they test them on each other. They do even pick up some of the architectures specifically built for COVID. And you can see the internal validation is pretty good with very high AUCs, but the external validation again drops. But then they looked at the saliency maps, and then they did this interesting experiment for using generative models where they start to make this COVID positive X-ray to be COVID negative and vice versa, and then start to look at where the model is looking at. And so what they show when in this generative task, if you can see that there's an R here, so if you move it somewhere else, I'll show you on the next page, they start to see that the models are mainly looking at the corners, just similar work like John Zek, trying to say, it just really tries to learn where is this image from. And in this work, they started to try and let's remove those radiographic markers. And they find that the model, when you remove a shortcut, it just moves on to the next shortcut. So which almost gives us this feeling that we have to almost be peeling back a mask or peeling an onion to understand how the model works. And in these places where they start to move, to change, to transpose some of the labels, for example, in this negative image, you can see the radiographic marker is here, and then this is positive image, and you can see that that's where the model still focuses on. And then one thing that they did here was and it's not unusual, to change the penultimate layer to predict something else. So in this case, they use a projection and patient sex, and they find pretty good internal and external validation. So in some of these models, it's really showing that they don't really learn the disease characteristics. figures out what's the shortcut. And in these cases where we provide differential care for some of our patients, the models are very sensitive about. And I hope that this still, again, convinces you why this is an important space to be in. This is similar work done looking at hip radiographs. Their data sets had a lot of things. The reason why I show this is that, they kept sort of visualizing and keeping, visualizing, multiple layers. And this type of data set that has this granularity are not available in the public domain. And it really remains one of the toughest areas for us to study shortcuts and the impact of shortcuts. You can see that for them, it really was the scanner model and the scanner manufacturer that were the most important factors in terms of what's going to be the outcome prediction. They do something interesting, which is to try and mix and match these cohorts and bring some of the characteristics to try and do the prediction. And I thought this was interesting because when they start to combine this model, patient factors, image factors, hospital factors, disease factors, that the model almost now gets to just randomness, chance in terms of its predictions. And this is because this line here becomes a useless model, because when you sort of start to change the confounders, you take away what the model was predicting on. So again, just some different work showing this work. This work, again, shows saliency maps. This is for pneumothorax. Here there's pneumothorax, here there's no pneumothorax. We still see the saliency maps in the same place, but when you look at, and this work also referred to hidden stratification as termed by Lauren, you start to see that the models usually perform better for patients who have test tubes. This is not what we care about most versus the patients who do not have test tubes. We've seen some other work where people have used autoencoders to try and change the space. In this work, they were trying to use shortcuts and then have the human say is this a valid feature or not. The reason I'm saying this is quite a lot of work is starting to do this, where they have the humans vet the image. I want to say that this is actually pretty challenging because, for example, they ended up figuring out that the position was the most important thing for COVID patients. And it actually makes sense because patients with COVID appear closer to the scanner, while patients with no COVID appear far away. And this is just from a radiologist's point of view. I don't know that this is how the image is acquired. If you are in the hospital, you're probably getting an AP view. It's farther away. You're in your bed. You're probably pretty sick, and that's what the model is looking at. And as we get into this new era where we're seeing new types of data sets, we've seen the foundation models, we're seeing embeddings. This is just recent work from Ben's group. And we're starting to see that those data sets still encode some of these hidden signals. This is the text expert model. You don't see, when they use the PCA for visualization, you don't see much of a difference in terms of the sex here. And when you see sort of the foundation model, fundamentally, you're still seeing that it's encoding male and female. Remember, these are just numbers. So first of all, on chest x-rays, you cannot tell the findings. You cannot tell that the insurance of the patient is blah, 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 or this is the race of the patient. And now you're adding in a numbers point. So still just be very careful about how you use this. And so, I want to, again, I started just introducing the different types of how people call this, association bias, table bias, confounder, shortcut bias. I think we do need to think about what's going to be one of our terminologies that allows us to jointly learn from other people when we're working the same. This is the fusion models. When you say dental assistant, they tend to be mainly female versus doctors. And this is recent work, actually, it's being presented in MICCAI, where it's trying to say, can we start to use this generative networks to tell us, what's the confounder, and you start off with an original image, you say, please add COPD, please add a hiatal hernia, make the lung have interstitial findings, alveolar findings, blunt the costophrenic angles, put emphysema or make the aorta long. And, and what they show then is to start to visualize the shortcuts. And for example, what they group is some of the biologic things. For example, you have an endotracheal tube, things that are done to you as part of treatment. So these are things that someone has added, and then looking at some of these characteristics. And they start to see, well, if you have a pleural effusion, really, it's mainly like they bring in, when you start to see what the model is doing, it starts to bring EKG, wirings, or, something else. And that's kind of, for example, if you have a heart valve, you can see, yes, you have the valve itself, but you also have these sternotomy wires, which, would happen if you're not having a minimally invasive way to place your valve. And so, then they actually do use radiologists to look at the labels and look at the diagnosis, and then see if the confounder is present, and what's the ratio of confounders. You can kind of see sort of like the treatment-related confounders that are present in their work, and what are some of what they call the physiology-related confounders, and how that changes. And so when I think about this area, which is an area that I'm very passionate about, I started saying, look, we have image-only models. They seem to be performing better. You don't need the intense labeling that is required for these other types of supervised classification. We're moving to a new era where we're seeing embeddings and foundation models being where we start instead of image pre-training with even ImageNet. They're efficient, they're computationally efficient. They minimize, for example, the work by Andrew from Google shows that you can only use 45 chest x-rays and you can get a good model for tuberculosis and pneumonia. And so we see these image-only models really accelerating, but at the same time, when we see one of the biggest pitfalls, we see these shortcuts and we don't understand them, if these shortcuts help us to create fair or biased models, and what is going to happen when we start to merge multiple data sets, and even not just imaging and other textual data sets. And how should we be thinking about the reader study? There's new work from Google that was trying to say, here is how we had the readers perform. This is the same way we've traditionally done reader studies. How can we get consensus around this? I mentioned that we're moving to this era where we're not just working with real data, we're working with embeddings, we're working with synthetic data and foundation models. And looking at intersectionality, for example, if this chest X-ray can encode race and sex, then you can imagine that those two now are merged together. And we know that, especially from the work from Lale, that this is super important in terms of thinking about bias. And then what explainability tools are required for us to really look at this, and what's a model building from at the design phase that allows us to say, hey, when you do this, this is most likely going to be a pitfall. Most of this work, I've said, relies on out of distribution model drop failure. But what some of the work actually from the COVID shortcut signals showed was that the external validation doesn't really work, and you can really miss the shortcut failure in those type of things, especially in this context of hidden signals. What does this mean for our data sets? How much more variables should we be providing? Should we just be giving you JPEGs or PNGs versus the original DICOMs? And I know one of the talks that is going to be here is going to show bias actually in a cardiac segmentation task. In the past, I always used to say, well, if you are in this space, please try and move. I know it's expensive, move to bounding boxes or segmentation to build models. But now if these are also showing failure, then maybe I need to rethink what my recommendations have been. And hopefully that this is not another shortcut, because I don't understand why just drawing circles around the hearts would have another shortcut that the model learns. I enjoy studying bias. This is the annual bias datathon from this year. I hope that some of you are going to come next year. We work on real-world MRE data sets and just have an amazing time tackling the same issues. And I can tell you that shortcuts was one of the themes. I'm always hiring and looking for postdocs, and here's my contact information. Thank you again for the organizers for inviting me. I apologize again that I'm not in person, but I hope that this gives us some discussion for a really enjoyable afternoon understanding how to mitigate bias in medical imaging.
Thank you, Judy, for this amazing presentation. I think there were a lot of important pieces of information there that leave us thinking about shortcuts when we are developing these models, especially when they are used in hospitals. So we have some time for questions now. Yeah, so Otherwise, I can start with one. So at the end of the talk, you started to mention well, Ben's work on foundational models and kind of moving towards this direction where we are going now, at least in the computer vision community. I'm coming from ICCB from last week, and I thought it was a language conference more than a vision conference because of all the work that was done on that. So I wanted to know if you have some thoughts about how maybe this new era of vision language models may start playing a role here, maybe helping somehow or not, or I mean, I don't know. Do you have any thoughts on how this multimodal data could be?
You know, so I think this is an open area for research. So I hope many people can think a little bit more about it. But I'll tell you that this this era of new foundation models, one of the things that we have to think about is the transparency. So you think about, like, if you've trained a model using the Google embeddings, it's actually pretty good. I was very surprised. We did this in the datathon. It takes a few minutes to train a classifier, you know, but if you think about the transparency even on the data set that exists for us to even say, okay, what could have the model been looking at? The data sets are proprietary, right? So unless you have some auditability, you know, again, with these vision language models, yes, they save us time there, you know, but we still cannot go back and say, okay, maybe this data set had this type of composition or different composition. I think just based on our work, we are really going back to rethink how we curate data sets and what level of metadata we have to provide to people. Because if I don't give it to you, just think about 2 years ago, before our paper was published, only the MIMIC dataset had race labels, right? So how can you, when we are blinded, because what we are saying is that, yes, maybe in Europe we are good, we treat everyone homogeneously, we don't collect this data, but these models are able to pick up some signal that correlates to some of these social demographic factors. So yeah, I don't think that the only thing to take away is we still need to do a lot of work. We've just started working in these embeddings. And the second thing is that we need to just maybe not be blinded that maybe with the embeddings that it's different. We just have to be explicit about the failure modes that exist for it. But I don't know that we know enough, and we may not even have the type of compute that would allow us to even generate those type of embeddings. At least I know our group doesn't have that.
Okay, thanks for the answer. Yeah, here, Ben, question. Yeah, better if you come to the mic.
Hi, Judy. Great,
Hey.
fantastic talk. Good to see you. So I was wondering what your thoughts is about the evaluations that we do, because eventually when we often look at performance metrics, we are left with whatever the label we were given is considered to be ground truth, but clearly it isn't, right? So I was wondering generally, what's your view on, like, how should we maybe better annotate data and maybe not starting to just put things into binary values of diseases present or not and so on, right? So yeah, just wondering what you thought.
No, you know, thanks, Ben. So 2 answers. One is my postdocs have me going back to label a subset of the Emory data set, and I came up with 50 labels for chest X-ray, and this is just like not too many cases. And the reason I was labeling them this way was just the same thing. If we're going to be this type of granular, for example, we have to link outcomes. And let me give you an example of pneumothorax. If you have to say, okay, I'm going to predict pneumothorax. Yes, we've known chest tube, not chest tube. That hidden stratification is there. But size matters, right? So mild, moderate, and large pneumothorax. And if you think about those 3 things, and even another thing, trace pneumothorax. And so if you look at trace, there's nothing that is going to be done. And so, and I do think this is something that I'm thinking about, and hopefully we'll come up with something in the next months on this, is we have to link the fairness metrics to outcomes. And because else we stop so much at the metrics that no one is ever going to implement these biased models, or, or people will be too afraid. But we need to think about what the ultimate outcome is. If we are saying it's segmentation of cardiac, MRIs, what's the ejection fraction? Because if it's 71 versus 72, it doesn't matter. It doesn't change the difference that you get. But if you're saying that I'm going to, to look at this metric, and especially when the label is bad, and you remember the fairness tree, some says, oh, do you trust the labels? I mean, even just in our own work, when we've looked at just the labels for the chest X-ray data set and Emory, we are finding out so many problems. And so I think we need to think about what is the appropriate taxonomy for us to think about hidden signals, or how to even come up with even a framework for evaluation, especially when you are not working with people who are end users. I think some of the things in my data set I was putting in was, for example, who had EKG leads. We've never, in radiology, would never consider those as support devices, but it's clear they affect the performance of the model so much. And we need to be having these almost small components that we check on, but we almost have to agree on some of those things and I'm just doing this because my postdoc asked me to label some data, and in the process, I started just exploding my schema for labeling. So we don't have even a direction of that. Yes, we've tried to label data sets with more people. And then I think it's a tough place. And I do think that we just probably need to link the labels with some outcomes. Then it makes it more standard. It doesn't matter what metric I choose because the outcome is the same. That's my political answer to that.
Thank you. Is there any other question from the audience? Yeah, here.
Hi, Judy. Thanks for your talk. I guess I was just wondering what your perspective is on, our field here with for medical imaging AI, because I feel like in the last few years, it's kind of evolved from more case studies of showing that certain models can be unfair in these ways. And then I think now there's been sort of a trend towards trying to understand why that happens, or investigating the internal representations of bias in models. So I guess I was just wondering what your perspective is on the next sort of directions for our specific field, and maybe what you think us as a community should be working on in the next few years.
Mm-hmm. Ooh, you're challenging me on recorded talks to predict the future, which no one can. But I believe that our world is going to be changed by foundation models, especially when it comes to these embeddings. I think they completely democratize how we train data sets, how we train AI models. I was very, very surprised to see that you can train a simple classification model in minutes. That if you just remember how much grind it takes, and that's going to propel us in new ways that, and Ben has started to look at some of this work, but we don't know, is it better for generalization? All those things that it's almost like we have to, this new form of data set that we have to go through again. The second area, I think that is going to be pretty interesting, and I encourage anyone who's looking at this to force yourself to really work more with subject matter experts, is really to understand the value of AI. And also the second portion of things is these human-machine partnerships. So the new papers, I think someone just sent me a paper before I got on, they're showing that the experts, you bias them and you make their performance worse. And so you don't, that's a pretty big thing. For example, if you have someone who has 20 years experience reading mammograms and now you're making them worse in their prediction, that's pretty concerning. And we do need to do a lot more work into when do you give the right thing? Like I mentioned, I used to say, yeah, you should just give bounding boxes or detect or segmentations, because as a radiologist, when you show me this is pneumothorax, I can agree or not agree. But in these classification errors, we don't know, do those have the same amount? So we have this automation bias. And then I think we also don't understand the effect of massive deployment of AI, because again, like you mentioned, most of us still, test a very narrow use case. We're not big. And so that's an area that we do need to understand, like what's the, is there a lifespan? What's the lifespan of the model? I can tell you in Emory, we have two models deployed. One is a triage model, trying to tell you this patient has a bleed, you read this study fast, and the stroke model. And the value of this is because we don't have enough radiologists, and you don't want the outpatients to be sitting there when they have a critical finding. That's really been the value of radiology. But we don't, does it work better or well? No, it doesn't, and so we need to really think more about real world deployment and the real world implications. It's a tough area to do work because you kind of have to do qualitative work, which is, interviews are very hard, and reader studies, and but I really do think that this is going to move the needle forward, in addition to also just, yes, we cannot agree, all of us in the room cannot agree on the fairness, what a fair model is, but I think if we link them to an outcome, it wouldn't matter what Andrew did or what I did or what you did in terms of the end result. Okay, we are already on time, so I think there was one more question, but if it can be a really quick question and quick answer, we can do that. Otherwise, you wanna? Okay, pretty quick.
Thank you, Judy, for a great talk. So you mentioned at one point that one of the papers, they were using, they found shortcuts for chest x-rays. And I was wondering, because models often see things that we can't see, and you kind of compared it to peeling back an onion, at what point are we actually getting rid of like medically important things that we think are shortcuts but are actually useful to the model? Because there are some things like, the R that you said in the corner, that obviously is a shortcut, but it gets to a point where there are things that the model knows better than we do. Yeah. No, and I hope I didn't rush my final slide, which I said we need to figure out biologically useful shortcuts and non-biologically useful shortcuts, and what's important for the model. This is still pretty early work. We're seeing some work, like, for example, skin tone didn't matter for melanoma. I know there's the paper from Google said that, but age definitely matters for chest X-ray predictions. And so I think it's pretty exploratory. But the other way I have also been thinking a lot is to use, if we got better probing tools, is to say, if the models can see these patterns, what is it telling us? And use that for hypothesis generation, and then design the study, instead of just trying to think about this lens of health equity with a plan for deployment, is to use this ability of the models to pick up patterns that are not obvious for us to use them to probe and generate hypotheses. So almost the reverse. But I don't know that we know where we are. We need to define what a difficult task is for this model before we say, okay, this is a difficult task and I can peel back the onion and basically be left with something and nothing, and not remove all the layers.
Thank you. Well, thank you very much, Judy. I want to thank the speaker again.
Thank you so much again, and I apologize for not being in person to hang out with some of my friends there. So
next time.
Thank you.
Yeah. So now we are going to move to the oral presentations. So Ben.
This one here.
So I have a degree in computer science, I swear. Great. So our first speaker is Nilesh Kumar, who will be speaking about distributionally robust optimization and invariant representation. Nilesh. Oh, and it should be shared, right? Before we. Again, I do have a degree in this, I swear.
Thank you so much. Hi, everyone. My name is Nilesh Kumar, and today I'm going to talk about our work on distributionally robust optimization and invariant learning. So let's first figure out what we are trying to solve. So as just what Judy was mentioning, there's lots of taxonomy on how you define shortcut learning. This is another way of defining shortcut learning, which we call spurious correlations. So spurious correlations are similar to shortcuts. Basically, you have some irrelevant bias features that co-occur with your main label and give you an illusion that they are a causal feature. So for example, in this image, where we are trying to predict if the lesion is malignant or benign, you have an extra marker, which is a bandage that you can see in the orange color that co-occurs with lots of benign lesions. And it may seem that whenever you see that bandage, it's a benign lesion. So this is our biased feature. And such groups of examples which follow this kind of behavior are called bias aligning samples. So why do we care about them? We care about them because neural networks that we use everywhere for most of the predictions are trained using something called empirical risk minimization, which you commonly see when you are trying to do gradient descent optimization. So you basically calculate average loss of your batch and update the gradients based on that loss. But this loss means that all the samples are weighted equally. So there's no difference between bias aligning and bias conflicting samples. And this makes the model exploit spurious features or the shortcuts, so that now you are making your decisions based on spurious features, not the core features or the actual features that should matter. So for example, if you come up with a sample like this, which is a malignant lesion in presence of a biased feature, the model might predict this is a benign lesion because it sees a marker that's only present with benign examples in the training data. So such examples are called bias conflicting samples. So we do have some current approaches that try to solve this. So as I was saying, the problem with ERM is that it treats all the examples equally. We could solve that by having some sort of weighting mechanism for the samples in our loss function. So the first thing could be our weights could be static. For example, our weights could be based on the representation of subgroups. So if you see there are some subgroups which are very underrepresented, for example, malignant with that bandage, you can upweight them in your loss function, so your model pays more attention to those. Or you could have something of a more dynamic approach, because as you train your neural network, the behavior changes. So you have something called group distributional robust optimization, where you basically assign different weights to each group. So for example, if your bias aligning samples are doing very well, then you have a higher weight for your bias conflicting samples. So if you see this equation, it's very similar to the ERM. The only different part is the supremum, where you're trying to maximize the loss in the first part. And the only way to maximize the loss is to assign higher weights to the examples that are bias conflicting. So this is mostly related to the decision boundary of the network. The other part of the network is the representation, the inner layers. So we could debias them as well. That, in other words, you want your representations to be more aligned with the actual features, but not the bias features. So we go through these approaches in the light of medical imaging, which are very different from natural data sets that have a lot more noise than some of the benchmark data sets that are available in natural imaging. So if you look at the data set on the left, it's Isaac skin cancer data set. As you can see, the top left, and only the bottom right one is underrepresented, where you have malignant with a bandage marker, and all other three are overrepresented. So if at test time you see something of that, the model might use the bandage to make a wrong prediction. Similarly, there's Fitzpatrick dataset, where the skin type is correlated with the diagnosis of the disease. So lighter skin types are more likely to have malignant, and similarly darker are more likely to have non-neoplastic. So for rest of the presentation, we'll mostly talk about the Isaac dataset because it has fewer subgroups, so it's easier to talk about it. But the paper has all the results for Fitzpatrick as well, and they both follow roughly the similar trends in terms of results. So the most important part is, how do you know if a model is deep biased or not? There are a few ways to check it. So we basically divide our metrics into different parts of the network to check how good they are doing. So the first thing is we look at the debiasing mechanisms. So as I said, there are two kinds of approaches. One is based on weighting. So we look at how the weights are assigned to different subgroups. And the other is accuracy of a subgroup classifier, which is other way to say that given representations, how predictive they are of the bias features. So the other metric is the bias in the decision boundary, which is basically performance. But performance is slightly more nuanced. It's not just looking at the overall accuracy, but you kind of look at the accuracy difference between your bias aligning samples and the bias conflicting samples. We look at it in two different ways. One is to look at the best subgroup performance, which would be a bias aligning subgroup. We anticipate that since that follows the shortcut structure. And the other would be you average all the other subgroups and see how it performs with the bias conflicting subgroup. But we still need to figure out how to validate our representations, if they are biased or not. They are probably the most trickiest ones from these three. So we use SOM MIPS. SOM are neural networks that are slightly different from the traditional neural networks that you see, which do loss-based optimization. Instead, they are like competitive networks where they are trying to preserve the topology of the input space, so you can better visualize your examples in a reduced dimensional space, usually 2D. And cluster priority, we will talk about this more once we get to the actual results, but it's basically saying that if you have subgroups that are very pure, that means your biased element is having lots of say in terms of distributing your latent space, which should be low if your model is not is deep biased. So now we have the problem, we have the data set, and we know how to solve the problem. Now we're gonna see like how we can solve this problem. So the first thing we see is the ERM model, which is like a standard deep neural network that you train. And as you can see, there's a big difference between the best performing and the worst performing group. So column 5th, this is a big number, and it's expected from an ERM model because it's trying to minimize the average loss and exploit spurious features which don't hold in a test set. So the other thing, the next thing we try is what I was saying. You don't read all the examples equally. You try to assign more weights to examples that are harder, so that you pay more attention to your bias conflicting samples. That's we do with importance weighting, which is simply to say if your bias aligning samples are more in your training set, they will have a smaller weight. And similarly, if bias conflicting samples are lesser in number, they will have higher weight. As you can see, there's slight performance improvement, but still doesn't help a lot. The next thing we try is more dynamic approach, which is GDRO. So instead of just using like static weights throughout the training, you use loss to assign weights to your subgroups. So naturally, if there is a bias conflicting sample which doesn't follow the shortcut, the network would have a hard time classifying it and would result in a higher loss. So you would assign higher weight to it, making sure that you learn it better in a better way. But you can still see there's still some, not some, but quite a lot difference in the 4th column. The best is still a lot better than the worst. We should be able to reduce this. So we take a step back and we look at the debiasing mechanism of GDRO. So the debiasing mechanism of GDRO is basically how you assign weights to your samples, subgroups. So if you look at the subgroups in the bottom, the malignant bandage one is the underrepresented subgroup. And if the GDRO is doing what's doing, it should pay more attention to it. But it's not right. If you look at the curve, it starts equally, but when it goes down, it's never upweighted. That means just using the loss as a surrogate to identify bias conflicting samples is kind of a problematic thing. So what GDRO does to solve this is it adds something called a group adjustment term, which is basically same as importance weighting in the intuition that the overrepresented subgroups are weighted less and the underrepresented subgroups are weighted higher. And if you see the difference between the graph on the left and the right, the red line has a lot more weight, which is the underrepresented subgroup on this. And it also shows in the results as well. So if you look at the worst group performance, it improves quite a bit compared to the GDRO only term. So we now know that the loss function alone is not enough. So we need something that we can use to make it better. So we look at the representations now. Before we look at the representations, there are some other methods that don't use spurious correlations, like knowledge about spurious correlations. They try to use loss surrogate as a kind of a mechanism to figure out which examples are problematic, and they just upweight them. But as you already see, even with GDRO, which uses this information, like the spurious level, and even then it doesn't perform well. Naturally, the other improvements over it that don't use this suffer quite a bit. So if you look at this method, just train twice, which is like a version of GDRO that doesn't require spurious labels, but it suffers a lot. So this is mostly because the benchmark data sets, most of the high loss examples are bias conflicting. But if you look closely in the medical imaging, most of the low performing samples aren't the bias conflicting ones. There could be some because they are just inherently harder to solve. So this doesn't really work. So now we look at the representations, if we can improve them. So these representations are from SOM plots. These different colors show different subgroups. And if you look at the purity, if the purity is high, that means the bias, it's very easy to identify a subgroup. And that means the bias information is there. So if you look at ERM, the purity is less than the GDRO. That means GDRO isn't really helping with the representations at all. So we try to find a classical invariance representation method, which is used a lot in removing the protected features like age, gender, and sex, but age, gender, and like some other protected feature, but it's arguably not utilized as much in the spurious correlation setting. So the idea here is you have a feature extractor in the green, and you have the main classifier in blue, which is trying to predict the main label if the lesion is malignant or benign. And you have a pink label, the pink classifier at the down, which is a domain classifier in our setting. It's like if the representations have the bias information or not. And they work in an adversarial setting. So the feature extractor is trying to fool the domain classifier. That means trying to hide the bias information from this classifier. So if you look at the representations for this method, then it improves slightly. But if you look at the numbers here, the DAN doesn't really improve a lot, especially compared to the GDRO with group adjustment. So we again go back, look at the debiasing mechanism of DAN, and we see that the accuracy classifier still has relatively high accuracy on some of the subgroups, which means that the DAN is not doing what it's supposed to do. It's not removing the biased information from these representations. And if you look at the method again, the DAN, it might work when your main classifier is not biased. But if you think of it, both your main classifier and the domain classifiers are using the spurious information to make their predictions. That makes that the feature extractor is outweighted by the loss terms from the main classifier and the domain classifier. So we change this slightly just to make sure if we can use this DAN better. So instead of training the main classifier with the ERM loss, we train the main classifier with the GDRO loss, which means that the main classifier doesn't use spurious features as much. And this really helps in the debiasing or removing the bias information from the representation. So if you look at the plot at the right, the domain accuracies are all over the place, which means that the representations don't really have that much bias information to utilize. And this also shows up in the proposed final model. When you use these representations, there's a lot less difference between the best and the worst group. So to conclude, loss-based mechanism might work for natural data sets, but they suffer a lot in medical imaging because our problem setting is a lot noisier than them. And the invariant representations, which in theory should work very well in removing these shortcuts, don't really work because the other part of the network also suffers from the spurious correlation. And therefore, we need solutions that don't only work on like the individual parts of the network, but both parts of the network or the data itself. That's all. Thank you.
Thank you. We have time for maybe one question. So I have one. Your optimization method, you're modifying the training mechanism itself. Is this possible to reconstruct multiple points of the trade-off curve, or are we have to retrain with this new reweighted?
Okay.
They
are changing at every point. So it's like at this point, the loss may be coming because of the like the conflicting examples, but later on the training, it's possible that this weight is more for some other example.
Thank you. Let's thank the speaker again. Okay, our next speaker will be Thorsten Kalb, who will be speaking about revisiting skin tone fairness in dermatological lesion classification. Actually, speaking will be Richard Old. So.
Yes, my name is Richard Old. I'm presenting our work on revisiting skin tone fairness in dermatological lesion classification. First of all, the problem of skin cancer. The talk before already talked a little bit about the skin cancer domain. So 1 in 5 people in the US is affected until age 70. And in 2020, we have an estimated 120,000 deaths because of skin cancer. But the good news is that early detection can increase survival quite a lot, from 32% to 99% in the case of melanoma, for example. And of course, deep learning and pattern recognition based methods are quite promising for earlier detection. However, as we know from the literature and other studies have shown that deep learning models can actually exacerbate societal biases. For example, one societal bias would be that the survival rates for white patients is quite a lot higher than the one for Black patients. And related to that, people like in Black skin color normally present likely with more advanced stages of melanoma. So if we imagine a deep learning model helping to diagnose, if, for example, that model does not detect lesions in Black skin, then that could cause further delay in diagnosis and could be even worse than without having the model. So in 2020, there was a MICCAI paper that showed or that reported basically that there's no specific correlation between skin tone and model performance, classification model performance. So we looked at this work and wanted to investigate it even further. The method of how to estimate skin tone, like the skin tone is based on the individual topology angle. That's the standard estimation method. And based on this, we can estimate ground truth labels, and based on the ground truth labels, we can analyze the fairness. So for this work, we used the ISIC 18 data set with more than 10,000 images, and it has several levels, so it's multi-class classification. The ITA is based on an angle that we can extract based on the luminosity and on the yellow chroma of images. And basically it's like you just have one number for the luminosity, one number for chroma. So we need to decide which pixel to focus on if we want to estimate the ITA. And then later on, we bin the ITA into different bins to give us the skin tone types. Once we have the skin tone types, the next step is to use to train a deep learning model to classify the 7 different labels. And we used a MobileNet V2, which it was important to us to use a model that is deployable also in low resource settings on handheld devices. Based on this, we can then ask the question, is skin tone distributed equally? Does skin tone impact classification metrics? And a model that is only trained on, say, light or darker skin types, is it able to generalize to the opposite and vice versa? So one question for the audience: do you think this is a rather darker skin tone type image or rather lighter skin tone type image? Maybe raising the hands for lighter skin tone types. Okay, I also raised the hand, so that's like cheating, but okay. So yeah, I would agree. It's a lighter skin tone type, but you can already see some difficulties in estimating the skin tone with this image because the hair on the image is dark. So some pixels will have quite dark, luminosity, and also you have the lesion itself. This is a melanoma that is quite dark. Also, you have an edge, which is often the case in these dermatological images on the lower left part. That could also be like making the ITA estimation having a difficult time. So the four say methods that we used from that we compared from the literature, I think the four most maybe like most cited and most used methods, and you can see here the estimations of the ITA. It is quite different actually. So the first method estimates a type 1, so very light skin, while the second and fourth estimate a rather dark skin type. I have to say that the third method is an adjustment of the second one that we implemented. So how do these methods actually work? The first one is based on a pre-trained segmentation model that segments the healthy skin, so that we then use the luminosity and yellowness of the only the non-lesion skin to estimate the ITA. The second one and the third are a bit different. So they are based on random patches of the image, and then the patch with the lightest color is taken. A few pre-processing methods are applied to remove, for example, the hair, and then the ITA is estimated either using the arctan or the arctan2. And the arctan, the normal arctan actually overestimates darker skin. So the last one is based on grayscale thresholds and on predefined skin color range thresholds, and also gives, based on these thresholds, a segmentation mask that is then used to define what is healthy skin to get the ITA. And here in the next slide, you can see, okay, like having the entire data set evaluated like this, with the different methods, we see that the distributions differ quite a lot, which is not good in the sense that it seems that ITA estimation methods are very sensitive to what you actually take from the image to estimate ITA. So, for example, the last one seems like a distribution where like the first type is very there's a lot of first type. The third one is also similar, and in the first two we have for example, the second one we have a lot of type 6, which I said before is maybe a bit overestimated, and the first one has a lot of type 2 and 3, but not so many type 1 as compared to the others. So how does this affect fairness if we look at fairness as skin lesion classification performance? So using the mobile net, this is the results that we got on the test set. Same test set, same model, just different skin tone estimations. So just the ITA changes here. And you see that for the first method, we see that type 5 skin is rather like the performance is lower. In the one on the right, RP2, we see that it's actually vice versa. No, that here we see that the light skin has a disadvantage in the classification. So and in the middle we have both light and dark skin. So what we see is that the results can be quite contradicting, and a high variation. Maybe this is not really that important if we are lucky, if we can train a model on very light skin and then it generalizes as well to dark skin tones or vice versa. So how does the skin tone data shift affect the performance? how do we do this? So the training set only has labels with ITA bigger than 41 degree, and the testing is like all the other images. And the baseline is just a random split without looking at the skin tones. And actually what we see here is, for example, if you look at the weighted F1 score, we see that for the first method, DLHSS, we see quite a good generalization. So there's not, like, the domain shift does not seem to be that much. But for the other method, RP, we see that there's a quite bad generalization compared to the baseline. So this also leaves the question open, is skin tone something that is easily generalizable for deep learning models? Of course, here we have a limitation that slightly the class imbalance changes between, because we have different trained test splits between the methods. So, okay, it's really like a single method does not give us a good estimate, it seems, at least if we compare it with others. So what we could propose is to look at several methods, and then just think about, okay, how could we combine them? So let's have a look at the two, say, best methods, the third one and the first one from before, and have a look at the images where they coincide, where they both say, like, these are dark skin tone images. So these are these two, type 4, 5, or 6. And these are the 8 images from the ISEC dataset for these characteristics. And are these like dark skin tone images? Probably we would argue rather not, but we can see like some problems here, like again the hair. We have here some blue colors. We have relatively dark images, but not necessarily dark skin images. So we discussed these images and a few others with the experienced dermatologist, and she told us that these images are definitely not dark skin tone types. So what does this mean for future work? And what are our takeaways? So first, there's substantial disagreement between ITA estimation methods. Fairness outcome depends substantially on which method you use. ITA estimation methods overestimate dark samples. And even today's largest open dermatology data sets, like the ISEC 2018 dataset, are too limited at the moment for conclusive fairness analysis. This has us questioning the models that are currently used in dermatology practice, because dermatology is a field where it's quite easy to deploy a model because the images are relatively small. They applications can run on your smartphone, and people can even use these without intervention with dermatologists. So we question if there's substantial bias in these models, and we question if there has been really a good way of even estimating this bias up to now. And that's also what we would like to propose for future work, that we definitely need a consensus method that estimates skin tone very robustly, maybe not even ITA based, or maybe just with having ITA as a component, but a little bit more complex method that is robust against, for example, varying lighting conditions, non-imaging artifacts like hair, dark edges. The non-healthy skin exclusion is an important part, and also the mapping from a single pixel or from the mean of all pixels to image level ITA. We also saw a few issues with that, so that's also something to have to take into account. Thank you very much. That was it for the presentation. You have all the code on GitHub. And yeah, if you have any questions, you can ask now or also send an email. Thank you.
Thank you. Let's open the floor for questions. Time for 1 or 2. Check the internet chat as we're waiting.
Great presentation. So you were always talking about ITA, But usually there is this kind of, when the doctors annotate, they use the Fitzpatrick scale, right? So how your conclusions relate to the, like, did you do this analysis of seeing how, because maybe you mentioned that, but I missed. Okay.
Thank you very much for the question. Yes, indeed. We also discussed the Fitzpatrick type with the dermatologist. And actually, what was interesting was that she told us that she estimates that based on the color of the hair and the color of the eyes, not so much the color of the skin, because it changes in different seasons, like winter and summer, especially in Spain. And yeah, but actually that's something that we proposed here for future work, that the large dermatology data sets should also have the Fitzpatrick type annotated. And what's important is that it's not annotated after the data set is acquired, because it's like the dermatologist also told us that it's not really possible having a lesion image to acquire the Fitzpatrick. Based on that, we need to see the entire, like the full person and the hair and the eye color.
Like the speaker again. And now for our last speaker of the first session, Carolina Piçarra, who will be talking about analyzing race and sex bias in brain age prediction.
Thank you. Okay. Hi. Thank you all for being here on this last day. So in the next 10 minutes or so, I'll be talking to you about this work I did in collaboration with Ben on the assessment of race and biological sex bias in brain age prediction models through performance analysis and feature inspection. So in the last few years, a lot of people have investigated the potential of this brain predicted age as a biomarker for several neurodegenerative diseases like Alzheimer's, multiple sclerosis, epilepsy, even some clinical risks like mortality. So a lot of people have been studying this. And first I wanted to give you just a bit of the intuition behind this biomarker. And so people's brain structures changes throughout life, and healthy aging follows this kind of specific trajectory, even within individual heterogeneity. And these changes are visible in MRI, and it has been thoroughly shown that deep learning can predict age from MRI images. But when does this become interesting in the context of characterizing neurodegenerative diseases? It's when we see that actually having a disease not only changes your brain structure, and so these healthy trajectories are disrupted by the presence of disease, and it can be correlated even with risk, for example. So that's a bit the intuition behind it. And so when we can predict age from a brain MRI, we can then calculate the difference between the subject's real age and our predicted age. And this is this brain age delta, and is essentially our model's error. But if you were one of the people doing one of the studies that I just showed, you'd get your Alzheimer's patient, you see their brain age delta is higher than your healthy subjects. And so you'd see, okay, there is a physiology factor here that is maybe correlated with disease. But the question I wanted to also make here is that I think it's important to understand if in the studies, if this physiology factor is actually disorder related, or is it due to inherent biological differences, like due to the subject's race or the subject's biological sex. And so because of this, and also as this biomarker becomes a more important clinical and the potential gets unveiled of it, we need to understand if it encodes any biases and what is there more to it. And especially when a lot of these models are trained on data sets that are very unbalanced regarding demographics. And for example, this is a table from a review paper on deep learning for brain age estimation. It has the data sets that are most commonly used in papers in this space. And we can see that the data sets are commonly from the UK, from the US, from Germany, Australia, and they are often very skewed regarding demographics, and this in practical being said, they are predominantly white. And so when models are trained in very unbalanced data sets, they might underperform for some of these underrepresented subgroups, and it's important to assess this. So what we did was kind of like a case study of one of the most used models in this task of ResNet 34 with some normalized T1 brain MRI images. And we used ICSI and CAMCAN datasets for training data, and these are fully collected in the UK. ICSI is 80% constituted of white subjects. CAMCAN, we don't have racial information, but it is fully collected in Cambridge in the UK. So we can assume that it is also predominantly white. And then we test on UK Biobank, and we divide our test sets in 6 subgroups in white, black, and Asian, and then those are further divided into female and male. And of course, regarding race, we are fully aware that this is a completely oversimplistic split, but it was kind of the split that was possible with the labels that we had, and especially with the number of subjects for the most underrepresented groups. So we train this model, we test this model, and then our question is this prediction fair for all subgroups? And so here we did 2 analyses to assess this. The first one was related to the model's performance. And to do this, we sampled all the subgroups with equal sample sizes. We did this to just ensure the robustness of the statistical tests that I'm going to present in a bit. So we sampled each subgroup, we calculated the MAE, the mean absolute error for the age prediction. And here we have, oh my God, sorry. I am like a teenage boy now. We have the results for that. And we have, so on the left, it's the absolute MAE. And we can see so the error bars are sampled 10 times, and it's the standard deviation of that. And on the left is kind of the relative difference and relative to the average MAE of all the subjects. And here visually we can see that the model performed worse for black males with the highest MAE, and then for white females it performed better. So less MAE, it's a better thing. So we can see this visually, but we thought it was important to make a more rigorous analysis. And so we went to see, okay, are these differences actually statistically significant? And to assess this, we did first a test to compare between all the subgroups, and we might be familiar with just an analysis of variance. We did the non-parametric version of that because our samples were not normal. And upon the rejection of the null hypothesis, so a p-value lower than our significance level, we conclude, okay, there are significant differences between our subgroups, but between which? And so we did some post-hoc tests, and we conclude, yes, okay, there are significant differences between the performance of the black subgroup in comparison to both Asian and white, and then between the female and male subgroups. And so the second analysis that we did was regarding the features of the model. So the question is are the features of the model biased? And to assess this, we passed the model's feature vectors through a PCA model to reduce their dimensionality. And essentially, the PCA projections consist of this new set of dimensions. They're also called modes, which capture the direction of the largest variation in the high dimensional space. So here we trained our model for age prediction. So we expect that in the first PCA modes, we will have the biggest variation in the features between each age subgroup. So here we have the results of that. I'm putting that just bigger. So each row is one PCA mode, and then each column, the first is age subgroups, then attribute is biological sex, and then race. And we can see what I was telling you before. The 3 first modes, we can see that the separation between age groups is different. And then those are the modes that we're most interested in observing if there are differences between the distributions of the subgroups. So then we look, for example, in the first PCA mode, in the first row, both the distributions for biological sex and for the race groups are quite different. We can see this visually. And for example, in the PCA mode 4, in the bottom, we can see that the race groups seem to be different, but because these in the age groups, we can see that this doesn't really, the distributions of the age groups are similar. Maybe this is not something that we need to be that worried about because these features seem to not be used for age separation. So we see this visually, but again, we wanted to see if actually the differences between the distributions are statistically significant. and so went on to do some statistical tests to compare each pairwise combination on all our attributes. And here we want to look at the first 3 PCA modes, because as I said, it's the ones that encode the age separation. And here we see that within the race subgroups, there are 5 out of the 9 comparisons are statistically significant, which is kind of in line with what we saw, the differences we saw in the performance. And then for between female and male, 2 out of the 3 comparisons are significant as well. So just for finalizing with some discussion and conclusions, the statistical tests that we conducted on the model's absolute performance revealed those differences, that of the Black subgroup underperforming versus both white and Asian subjects. And then we saw differences between male and female. And one possible explanation for this is that these are exactly the subgroups that are most underrepresented in our training data set. So this might be a justification for that, but we saw some differences in the features, so we could investigate this further. And then the main limitation of our study is that we used only one model, one type of input features, and one combination of data sets. But we hope that this case study is further motivates a more systematic analysis of other types of models, other input features, for example, white matter and gray matter maps that maybe, like Judy was saying, sometimes you can just classify race from images. So maybe if we use segmentation maps, that might help. You can see that, and other combinations of data sets as well. Just coming back to what I said in the beginning, current research focuses a lot on assessing the correlation between this brain predicted age and neurological disorders. And for a lot of the studies, the differences between healthy subjects and these subjects is 1 or 2 years. And so in this physiology factor, I would believe it's important to understand where is this coming from. Is it actually from the disease, or is the prevalence different for subgroups? And it's important to investigate that. So we hope this further motivates people to assess their models and to see what is happening. That's it. Thank you.
We have time for questions. I guess I can start.
Yes.
Speaking to the microphone. Yeah, thank you for a wonderful talk. I had a question about, well, we know that many brain age models have biases in the residuals before we think about race and other subdemographics. How could we account for this in these types of analyses, like that perhaps that the demographics are not evenly distributed by age already, and so these biases are somewhat entangled?
Yes, you mean them being biased on like predicting younger subjects, okay. Yes, I think this, so one thing that we have in the paper, and I think I have here in the next, so I think it's always important to understand the age. So this is just the age distribution per subgroup. And I think you can look at that and see if the age distributions are similar. Maybe if they're not, that's something, I don't think I have an esprit on actually in practicality how to then take that into account. But I think assessing exactly what is your situation and on the methods for the correction of this bias, that might be because if you correct for this bias, maybe you're correcting for differences in age within those subgroups. But yes, I think the most important thing is to be conscious of what the changes are. And there's for example a lot of so we included actually these plots because there's a study that shows that if your age range, so if the age range of your training set is different from the age range of your testing set, that changes the metrics wildly, like it changes them a lot. And so it's also important to see if the age, not only the age range and the age distribution within subgroups, but even between training and testing set. So I think it's always important to assess, and that's why we included these plots in there for people to see that the distributions between the subgroups are actually similar. And so we thought that would be valid.
Thank you.
Yes, of course.
And so?
You go.
So, speaking to the mic.
Yes.
Sorry. So
when you use these models in real life, because I guess these models are used in real life, like this kind of predicting the age to see the gap and doing some kind of diagnosis with that. Do they define like this kind of threshold of whether this is healthy or disease or whatever based on the subgroups, or do you know if it's like this kind of thresholds is put like one for everyone for all the groups?
Subgroups like race subgroups or
Yeah, do you know if
men or
this is
women?
taking into account when defining the threshold? Because seeing that, if they don't do that, it's even worse.
I don't, and I think it would never be used like for a direct, for a direct diagnosis. I think it's more of a guidance. I don't think, from what I've seen on studies, it's comparing healthy to diseased, and so I don't think it has been a lot taken into consideration. That's also why we decided to do this assessment. But I don't think it's yet used really in clinical practice. But I think it would be important to, yes, understand if the threshold needs to be different because of differences. But we will have a discuss in the post, like maybe if you in these models you also input the information, the demographic information, maybe then you won't need to do it because the model is aware of information. But yes, but I think that's definitely a good point.
Let's link the speaker again. So speaking of poster presentations, we have our poster power pitches right now. So you can find presentation. So we're about 5 minutes behind, and we will simply break slightly later for coffee, but I'm sure there'll be plenty for everyone.
So I'm missing 2 people to send me the poster pitch. So if you haven't sent it, please come with a USB or something.
Is Chenwei Wu here? One of the other authors of presenting, Emil. You have 1 minute, and I'll stand ominously behind you.
Very cool. Hi everyone. Yeah, my name is Emil Gitman-Jelks. I'm one of the co-authors of this paper on the de-identification and obfuscation of gender attributes from retinal scans. So the retinal fundus images are very accurate biomarkers. So the goal of our research was to de-identify these images, or at least obfuscate the patient's sex from them, in order to mitigate the privacy risks associated with public release of data sets containing these retina images, and mitigating the risk for producing biased algorithms for the automated detection of diabetic retinopathy. We applied differentially private algorithm to both the entire image and also segmenting just the blood vessels, which are the parts that are identifiable or personally identifiable information in the images. Yeah, it's a minute.
There's multiple slides for this.
Yeah, sure.
Okay, could we have Sophia Martin? Sophie Martin. Okay. Maria Lara. That's you. Okay.
Yeah, that's me. Okay. So this is 30 seconds. Okay. So yeah, I'll be presenting the poster of Agustina, who couldn't be here because she gave birth like a couple of months ago. So in this poster, what I'll be talking is basically, imagine you want to audit bias in terms of calibration performance, not in terms of discriminative performance as we usually do. So if you do that, you have to be really careful with the sample size. When we analyze fairness in general, we have a minority group and a majority group, right? Usually a minority group has less samples, the majority group has more. Metrics that we usually use for evaluating calibrations are biased with respect to the sample size. So it's really easy to see fake biases when you do this analysis. In this poster, we basically show that with synthetic and real experiments. So yeah, that's
All right, and next we have Rebecca Stone.
yes.
Yep.
But I'm not Rebecca, but she sent us the text. So polyth segmentation is a challenging problem due to the variability introduced by different medical centers and acquisition methods. We present novel loss function for segmentation, which leverages the epistemic uncertainties from a Bayesian neural network to encourage the model to learn underrepresented sample regions. We show through testing on challenging tests that this approach can improve generalizability. Welcome to check out the poster and contact the primary author who could not be here as well. Thanks.
And then we have Nina Wang, someone who will be online. Nina, are you here?
Yes, can you hear me?
Okay, you have the floor.
Yeah, hey everybody, my name is Nina, and I'm sorry that I'm not able to be there physically. Have you ever wondered what causes bias in deep learning models? So in this work, we investigate the cause of bias with a case study using just X-ray automatic diagnosis. And for some of the disease, we even observed that even when training with only female samples, males still got better performance. So we tried to dig into the question by investigating 3 most discussed causes: imbalanced data set, physiological difference, and the label errors. So please check out our poster if you're interested, and you can also talk to me by scanning the QR code in the poster. Thank you.
Thank you, Nina. Yan Dang for our wonderful replacement.
Yeah, sorry. So I'm presenting this quickly on behalf of Bien from University of Barcelona. So I read a bit, I'm sorry. While 3D CNNs promise advanced diagnosis of Alzheimer's, a vital question remains: are they equitable for everyone? Our study highlights challenges like varying brain structures across ethnicities, gender-driven AD symptoms, and the influence of age and cognitive reserve. The inherent issues of 3D CNN, such as overfitting and data sensitivity, further compound these challenges. But the central point this paper investigates is the auditing and understanding the distinct and overlapping impacts of classification and calibration biases. While each has its distinct impact, such as classification bias influencing prediction accuracy across subgroups, and calibration bias affecting prediction reliability, the two can often converge and leading to intricate patterns of misdiagnosis. So that's, please contact Win, and yeah, please check out the poster.
All right, we have Masha Dibaji.
Thank you. Hi everyone, I'm Mahsa Dibaji from University of Calgary, and our paper was on the effects of sex-related differences on brain age prediction using brain MRI. And as you know, there are some sex-related differences between brain volumes from males and females, and that could potentially lead to unfair and unbiased outcomes when predicting brain age. And in our study, we developed an experimental design to compare the models considering sex and dataset variabilities. So we used 2 datasets and trained 3 models using each of those, 1 trained on females, 1 trained on males, and 1 trained using all of the subjects. And then evaluated those on 4 sex-specific test sets. We saw that dataset variability and also those sex-related differences impact the results, and also models learn different features, even those showing similar accuracies. Thanks.
And we have Tiana Lee.
Well, firstly, I was expecting a PowerPoint. So yeah, I'm Tiana Lee. So as Judy mentioned, and everyone here has mentioned, bias has been demonstrated in a lot of different organs and imaging modalities and applications, but it hasn't been shown so much in cardiac MR segmentation. So that's what I'm focusing on. My previous work has shown some racial bias in CNN-based cardiac MR segmentation. And we want to expand this by not just looking at the one model that we used before, NNUNet, but expanding this to 3 other models to see how dataset imbalance affects segmentation performance and how it differs between those 4 models, with the hypothesis that a more balanced training dataset will produce a more fair result. But was that true? Come to my poster to find out.
And apparently you're staying up here for the second one. Yes.
And I'm also sometimes Mohammed. I was also one of the authors here. So for this paper, we were looking at breast cancer. And so machine learning models can be used to predict tumor molecular subtypes using radiomics that are kind of defined defined using contrast enhanced MRI. But again, as Judy mentioned earlier, there are some differences, racial differences in tumor and breast tissue characteristics. So we were looking at whether those differences can also be seen in radiomics and whether machine learning models can predict it. Generally, these sorts of distributional shifts are shown more in deep learning than classical machine learning. So we were using random forest models to look into that. And again, if you want to see the results, come to the poster.
Hello everyone, I'm Devinda. So in this research, we'll dive into how to analyze longitudinal data. So longitudinal data is important for disease diagnosis and treatment efficacy. However, the handling of the data can be so complicated, and therefore in here we try to focus on assessing how data splitting strategy during cross-validation can affect leakage, data leakage and biases. And our findings found that certain data splitting strategies can affect the data leakage. And through graph visualization, we found that these biases can further impact on identity confounding or shortcut learning, where the deep learning models not only learn the diagnostic features, but also the subject or identity information. Well, if you're interested in this research, feel free to come to my poster session later. Thank you.
I believe that concludes our power pitches. So thank you all. We'll see you down at the posters.
And remember to vote.
Oh, yes, remember to vote.
And to be back at 4? I think it's at 4, right? Yes, we have to be back at 4.
Right, good. Thanks and welcome back to the second oral session of the FAIMI workshop. My name is Ben Glocker from Imperial. I have the pleasure to chair this session. And we have 3 exciting talks, and the first one is on bias and unsupervised anomaly detection by Cosmin, please.
Thank you, Ben. So my talk is about bias in a bit of a new domain. So it's anomaly detection. And we tested on a test case on Alzheimer's detection on brain MR. First, before we go in the exact topic of the bias, I want to at least clear a bit the motivation, why we do anomaly detection and how it works briefly. So if you look on the right, you'll see a plot of increasing exams, as are CT exams and MR exams. And the plot or the line of the medical graduates quietly stays the same, doesn't grow at the same rate, meaning that they are overwhelmed to process a lot of data very fast and very accurate. And we need to help them somehow to do that with automated methods. And historically, supervised methods were used for that. But if you look at the distribution of diseases, there are a lot of rare diseases, and albeit they are rare, they affect a lot of the population, about 10% of the population. So, meaning we cannot annotate so many new cases, new diseases. That's why we need an anomaly detection or unsupervised method to find these anomalies. How it works, instead of having labels to find the specific disease, instead try to learn the normality given a set of healthy images. For instance, learn a representation from them and then reconstruct from this representation with minimal error the inference sample. Now, what you expect when you get an out of distribution sample is to extract kind of the same features that you are learned to do. And then when you do a difference map, you would see high response where the image is anomalous, or yeah. In our case, we looked at Alzheimer's, so it's actually more important than finding Angelina Jolie. And what you see on the top is an input with an Alzheimer's case. So you see some atrophy happening in the Sylvian fissure there, and the reconstruction just replaced this atrophy with healthy tissues or gray matter tissues. And if you do a simple difference map between the input and the reconstruction, you would find the anomaly highlighted. So this is how it works. So it sounds great. There's no issues. You can find any anomalies. But of course, if you train on a specific distribution, be it healthy, you're very susceptible to any domain shifts, not just pathological domain shifts. This can be scanner, race, or sex domain shifts. And I wanted to evaluate that. Are these shifts bigger than the pathology shift? Can we still find pathology if you have these shifts in the training and test distribution? And just to compare what kind of bias you'd expect in unsupervised methods, I have this comparison to supervised method. This is a work by Esther, where you are trained to find the target anatomy with labels. And then the issue is when you evaluate on protected or underrepresented groups, you will have lower performance, a performance drop, which is not so bad, so it's slightly, but still significant. Then you try to mitigate this difference in performance. Now, with unsupervised anomaly detection methods, you have different kinds of losses, of biases. I will show it in a second. This is how we set up the experiment. So we trained on ATNI. We picked a white female Zeeman scanner because there was the majority of class, so we had more images for training. And then we have the baseline, which is kind of the first row here, where you have the test from the same distribution. So there are no shifts besides the pathological shift. You have control and Alzheimer's, but the rest is the same. You still have white female Zeemans. And this is our baseline performance, how the method works. And then we try to introduce one non-pathological shift at a time and see what happens. These are the results. So you see some violin plots here with the left, the baseline. So what you expect is this blue part of the violins to be low. This is the error on healthy images. And the oranges part of the violins to be very high. This is the anomalous set of the images. So if the error on anomaly is high, it means you can detect it. And if the error on the healthy is low, it means you can accurately restore it from your latent representation. Now, you can see two different types of biases, and one I call it the naive bias. And what happens usually, we don't have access to healthy and pathological data set from the same distribution. So people train on some healthy distribution where we have a healthy data set and then evaluate on a completely different distribution, for instance, BRATS for brain tumors or MS lesion in some other distribution. And the issue there is, if you can imagine, you can take the blue part of the volume from the baseline, which is your healthy distribution. And if you take now the orange part of the volume from the male, so the sex shift, you'll be very good in detecting it because the overall volume for the male is higher, so you make more errors. But this will be also the case if you take the healthy from the sex distribution, you would also be very good in detecting this as Alzheimer's. I'll show some numbers in a second. So the bias in this case is visualized as a shift of the whole violin compared to this mean error distribution of the baseline. And the second bias, and this is more the algorithmical bias, is what happens if you have in the test the same distribution. So you have healthy and anomaly from the same distribution. How does the bias then, how does the algorithm perform? Do we still find the pathologies or not? And this is visualized as a shift inside the violin. So if the blue here goes up and the orange goes down, it's bad. And that just shows some numbers to summarize it. These two tables show the two types of biases that I was talking about, and red here means bias. So as you can see, it's kind of a lot of red in the table, meaning the results are really skewed by the bias. And I want to focus on the metrics as well. So if you choose, for instance, the area under the rock curve, when your data set is completely imbalanced, you might miss that there's actually a bias there. So just the precision equal curve is much more better from that, and we'll focus on this for now. And for instance, if you look at the male, which I showed earlier, you'd have an increased performance on the left compared to the baseline. So instead of 65% accuracy, you say, oh, it's great, we can detect Alzheimer's with 90% accuracy, but accuracy detection. So to sum up, if you have an algorithm that was trained on one distribution and you perform the pathology test in the same distribution, would have a baseline performance of 65%. And the goal of this work was not to really do perfect Alzheimer's detection, was just to show that there's a bias in the distribution. And once you have other non-pathological shifts, like a scanner or sex or race, the performance drops considerably. And this is the algorithmic performance. So the one where you have the healthy and the pathology from the same distribution. In other words, other domain shift or other out of distribution shifts are more important here than the pathological shift, or bigger than the pathological shift, which makes it challenging for developing unsupervised anomaly detection methods. And it's making challenges because you have to do two things. You have to be very able to do domain generalization on different domains due to scanner shifts, sex shifts, race shifts, but you have to be very sensitive to pathological shifts. So you cannot use the usual domain adaptation methods that take a new domain and then try to adapt to that, because then you also adapt to the pathology, and you don't want that. So this kind of contrastive loss of being domain agnostic to a lot of things, but very specific, very sensitive to pathology, is very difficult to achieve. Thank you.
Thank you very much. Any questions from the audience? I would have one immediate question. So you showed some nice data coming from different kind of domains, including different scanners, and often, especially in neuroimaging, we do data harmonization, trying to get rid of scanner differences and so on. What's your view on that type of approach when it comes to differences between the data sets? So if I try to harmonize between Siemens and Philips, do I need to take care also about the mix-up of, or the make-up of those data sets in terms of other characteristics when I apply data harmonization technique?
Yeah, thank you for the question. You could apply data harmonization, but then you would have to know what you want to be domain agnostic to. So you have two scanners like Siemens and Philips. You can harmonize the two scanners. But then it's the question, how will you generalize well to new scanners that come? Or for me, what was even more important is when you learn this normative distribution, how well do we learn it? Do we learn like for protective groups as well as for the other groups? And their harmonization, I guess, it's not so helpful. And so I think if you want to generalize well, you don't have to introduce any expected harmonization or what to expect to. Or there are two ways, right? You can try to make the data more similar, or you can try to make the algorithm more working more better for different classes.
Any other questions? No, then let's thank Cosmin again. Thank you. Great. And now we come from bias in unsupervised methods to unsupervised bias in other methods. Is that fair to say? Let me find your presentation. Good. Over to Enzo.
Okay. Thank you, Ben. So, hi, everyone, again. So I'm presenting on behalf of Nico, my PhD student who will be here today. Yeah, we will be talking about unsupervised bias discovery. So You know, in this workshop, we have already discussed a lot about potential biases that may exist in different contexts, gender bias, underdiagnosis in different settings. Here, we will basically look at segmentation biases that, as Esther showed in her paper a couple of years ago, it exists. And here we have cases that was shown before, actually, where, for example, for different ethnic groups, you can have different type of DICE score, right? For a segmentation model in cardiac images here. We have also observed this type of biases in age, for example, when you are segmenting structures on X-ray images like the lungs or the heart. And this is actually the type of images we will be looking at in this study. So how do you do when you want to audit bias? You usually take a model, like in this case, a segmentation model, and you basically take groups and you evaluate your model in these groups, in this case, for example, male and female patients, and you compute some kind of fairness metrics, usually a gap in terms of DICE, in this case, or Hausdorff, or some other metrics that were proposed there. What's the problem here? We need ground truth. In these cases, we need ground truth. But we know, and it has been shown by previous works, that actually fairness sometimes may not transfer across distributions. So if I have a new data set, a new distribution, and I want to evaluate whether my model is biased or not, I will need ground truth for doing that. The question that we try to answer in this work is, can we anticipate biases in segmentation models without having any type of ground truth? And for doing that, we basically propose a solution that is based on Ben's paper on reverse classification accuracy. So reverse classification accuracy is a really simple framework that I'm a big fan of, where you have an image, in this case, and you have a predicted segmentation, okay? And let's say I want to estimate the quality of this predicted segmentation, but I don't have ground truth for this case. So I have ground truth for another kind of, for a reference database where I have a lot of images with the corresponding segmentation, okay? And so what I'm gonna do in this case is I will, well, first take the most similar images in our implementation to the one I'm trying to segment and register in a deformable fashion my image to every one of those in my reference database. Once I did that, I will transfer the segmentation that I predicted to all of them. And I will compute, so this is the transfer segmentation, and I will compute DICE or Hausdorff between the transfer segmentation and the segmentations I had in my database. The intuition here is that if the image I'm evaluating is well segmented, then it should be good to segment, I mean, when I transfer that, it should be at least be good to segment some of these other images that I had in my reference database. If it's bad, it's not gonna be useful to segment any of those images, okay? So when doing that, you will estimate this RCA DICE estimated coefficient. And what we analyze in this paper is whether we can use the gap in RCA estimated to measure biases in new populations for which we do not have ground truth, okay? And so in order to do that, we designed some experiments to validate this idea. And the first one was really synthetic in the sense that we took a bunch of images coming from different X-ray databases like JSRT, Montgomery, Jensen, etc. And we trained a unit model for segmenting lung and heart in these images, okay? These are X-ray images. But what we did, it was while training this unit, we were saving the weights along the training. So what we have is 12 different models now with different quality of segmentations, okay? And what we did to simulate this scenario of having two groups where one of them have really like low quality segmentation and the other one has really high quality segmentation, it was to say, okay, let's take, for example, male and female patients, and I will segment one group with one of the units, like the one that is really bad, for example, the first one, and with the best unit, that is the last one. Okay, so in that, for the male patients. So in that way, what we are doing is saying, yeah, for example, we have a case in which male patients have really good segmentation and female patients have really bad. A really synthetic case because we made it from these cases, but it's just for evaluating. We will consider that these segmentations are somehow coming from the same model here, and we will see if we can capture this bias using our unsupervised method based on RCA. And what you can see here is what it happens when you measure the gap in dice coefficient using ground truth, okay? So here I have in the x-axis there, the female population that was segmented with units of different qualities. Sorry, remember that the bigger the number of the unit there, the better the model is. And the same on the y-axis, but for males. And what you see is that in the diagonal, the gap is almost zero, basically, or close to zero, because both were segmented with the same quality of unit. Okay, but in the other cases, the model is biased with respect to male in red or with respect to female in blue. Now, this we computed using the ground truth. And this is what you compute when you use our, basically the dice estimated using RCA, okay, the same gaps. And the tendency is really clear. Actually, if you look at the correlation between both errors, like the estimated and the real, you can see that it's really well correlated, not only for dice, but also for household. So it basically shows that you can capture these biases, at least these extreme biases that we were seeing. But then what we did, it was to take another case, and we say, okay, let's now go to a bit of a more real scenario, where we have one model trained, and we test on female and male separately, okay? But we had two models, actually. One training only on male images, and another model trained only on female images. Okay? And we segmented both groups, and we observed whether there were variations there and whether we could capture them or not with our method. So here you see, for example, for the case of heart, something that was interesting for us as an observation that was that even in this case, for example, if you look, we have models trained on males on the left and model trained only on females on the right. And in both cases, we got better performance on female. Okay, that's something we were not expecting. We were actually expecting to have like differences, but no. But the interesting thing is that actually when you do the auditing using the estimated dice, the RCA-based dice, you get kind of the same, you can capture these biases. And actually there is still a strong correlation in this case. So this is basically the idea. It's really simple. You use this framework and it can help you to anticipate existing biases. We then use this at a larger scale. So this is a different work that we did where we wanted, so we had this segmentation method for X-rays that we are really proud of, that is really robust. So we say, let's use it for segmenting a lot of different data sets. We wanted to create a new data set that we call CheckMask. That is a data set where we took all the big X-ray segmentation, X-ray image data sets like Mimic, chest X-ray, all of them. And we segmented them and we released all these segmentations. But we also wanted to release some kind of quality metric with every one of these segmentations. So what we did, it was, we took the segmentation data and we estimated using the RCA, the dice and the Hausdorff for every one of those images that we are releasing. So you can go now, take the segmentation and have an estimate of how good the segmentation is. This is the data set and it's available online actually, so if you want to access. But what I wanted to tell about that is these plots that we created afterwards. So we tried to use this idea of analyzing bias. In this case, of course, we didn't have segmentations because these data sets are open data sets that we actually augmented with segmentations, but there are no manual segmentations for that. And we did this analysis of looking at the estimated dice. Is the only thing we can look at here because we don't have like real dice. And something interesting, it was that, for example, here you can see the dice coefficient for patients, for images captured on posterior anterior or anterior posterior view. Okay, these are like two different cases. And something that is pretty interesting is that images, the anterior posterior images, okay, these are usually coming from people that are hospitalized because it's the way in which it is captured. And if you look at the dice coefficient, it's much lower in general than the dice coefficient for cases that came from PA, patients that in general go and just stand. And this is something that makes sense. And it was possible to discover this bias using this technique based on RCA. So this is all basically. In conclusion, we show that this method, RCA, can be used for estimating biases in unseen populations. One limitation of that, of course, is that here we are talking anatomical segmentation. In this case, RCA works really well. Now, if you go to lesion segmentation, RCA is not maybe, or at least this version of RCA is not the best one to go. And so you could not be doing that. And we validated this in a different, in a couple of scenarios. And yeah, and you can use it basically for that. So that's all.
Thank you very much, Enzo. It's great to learn that RCA has a fan base greater 0. I didn't realize that. So yeah, first of all, questions from the audience? Yes, please. Then. Do you want to come? So
walk in here, so you have to...
Okay, I can repeat the card.
So first of all, thank you for talking. But also, I guess, do you think the results move the individual model? So we are testing using RCA, specific UNet models, and you have 16 of them. Does the ensemble result tell us about model 7? Really great. Does it speak something about the actual training data set to the district?
I'm not sure if I get right the question. I mean, in general, when we audit a particular model, right? So the conclusions you will get with this are the conclusions that you are drawing for the particular model that you are auditing. In this case, it's not something that will generalize, I think. Or maybe yes, but I don't know. You think it may generalize to other cases?
Well, I think unless we know something a priority.
Mm-hmm. Okay, we can talk about that later. Yeah. Yeah. So the question is whether biases in the registration model may somehow permeate into the analysis that we are doing. Maybe even when it's better, because it's RCA basically. It's a thing from RCA, but we have analyzed biases on registration methods, and actually we have not found them. So like at least some biases that we were seeing in classification, we took the same for sex, for example, and we took the same setting for registration, and we couldn't find biases there like really clear. So to me, somehow it seems that registration models seem to be a little bit more robust to that. I'm not sure, but for sure, if there is a bias in your registration model, it may somehow permeate here. So you have to be careful with that, of course. Yeah, but I think it's a really good point. Okay. Okay, thank you.
Right. That gets us to our last talk as part of FAIMI, I believe. I maximize the space for you. Great, Amar, over to you.
Thank you. Hello, everyone. Thank you for your patience for the last talk of the day and hopefully of the conference. I'm Amar. I'll be presenting our work on debiasing counterfactuals in the presence of spurious correlations. So let's jump right into it. The motivation for doing this kind of work is a very simple message that all of us are doing deep learning, and if you see or think a bit about it, deep learning models optimizes for majority of the population. What this means is Given a data set, deep learning models are easy, or they can easily learn shortcuts. For example, consider a data set where all the sick patients have a medical device and all the healthy patients do not have medical device. And few of the sick patients do not contain medical device and few of the healthy patients contain medical device, basically cross off what I'm showing here. So if that is the case, and I tell you to design a deep learning model, you will go with your favorite optimization technique. And what this deep learning model will learn is disease equals to medical device. What that means is whenever there is a disease, instead of looking at the disease, the optimization approach, because of the optimization approach, it starts looking at medical device. Now, the next part is we need to verify whether it's looking at medical device or looking at something else, which is shown by this method of explainability. And the approach that we use is counterfactual generation, where we try to show the model is right for wrong reasons or right for right reasons. Either way, it holds the point. So over here is two different images. The leftmost labeled as A is a real example of a sick subject. And as I just explained, sick subjects are those with medical device, shown in this cyan boxes. On the center image, you have a counterfactual image of a subject who is classified as healthy. So if you're familiar about this work of counterfactual images, essentially you try to synthesize image that belongs to a different target class. In this case, the real target class is sick, the counterfactual target class is healthy. And if you take a thresholded difference map between the two, which is essentially trying to analyze what is the classifier looking at, in this case, it flares up in the region where you find medical devices, which means that classifier latched onto this spurious correlation rather than latching onto the disease pathology. So a bit of background about this. There are two different domains that I have tried to combine in this work. The first one is debiasing, and there are a lot of debiasing methods that is available out there: stochastic weight average density or sharpness aware minimization. In addition to that, we have a lot of explainability methods available, such as GradCam, LAM, Shipe, Gibbsplanation as well. In addition to that, a lot of work by Ben Glocker and his group, and in fact, AtriNet, which was also quite popular in terms of post-hoc explanation. So what is the difference we are trying to point in this paper? We are not only trying to debias, but explain that what is the debiasing approach looking at. And that's important, as I said, because you need to know if a model is making a decision. Is it the right decision associated with the disease, or is it just a decision? Because if it was just a decision, it's very easy to fool a classifier using an adversarial attack. So that's the message for the paper, which is explainability via counterfactual images, and we try to debias the result. In summary, if you ask this very simple question, can a model be trained to disregard spurious correlation and identify generalizable predictive disease markers? And I'll clear this point, why generalizable, in a minute. So the data set that we look at in this case is RSNA pneumonia detection challenge. And in this case, we try to prove our point using synthetic artifacts. What that means is we created 4 different classes, as I just explained. On the diagonal terms, if you look at this matrix kind of image, it's shown as 6 subject with visual artifacts shown in cyan boxes. And the bottom diagonal term is the healthy subject with no visual artifact. And those are the majority classes because that's the major prevalence of images. And the off-diagonal term are minority subgroup, which is just showing a different nature than the sick and healthy subject, which means that few of the healthy subject will have this artifact, and few of the sick subject will not have the artifact, and that few is 1/10. So the ratio between the majority and minority is kept at 1/10. And we also show our result on a real artifact, which is medical devices. And this is for the Chexpert data set, where we look at medical devices. Again, the same explanation. Majority of the patient who are sick have the medical device, and majority of the healthy patient do not have the medical device, and cross relations to this. So the methodology that we use is this end-to-end training. So we propose a method that is trained end-to-end, which first debiases and second explains what is this debiased method looking at. And in terms of the contribution, we also show an evaluation method where we propose a new score, which we call as spurious correlation latching score. And the need for this new score is because all the other method for evaluation available out there in the literature does not address the point that we are trying to make. So this method of counterfactual generation is done via cycle GAN, and that's the usual architecture for a cycle GAN. What we have over here is two different domains. One is the domain of sick patient and the domain of healthy patient. These domains are separable. And what happens is at the training time, simultaneously, two different samples are taken, the unhealthy sample, which is sick, and healthy sample. And these samples are passed through their respective generators. And these respective generators are such that if your input image is sick, it transfers into domain where your output image, which is the counterfactual image, will be healthy, or vice versa. Now, what's interesting is this centralized place black box classifier, because if you try to use different classifier, you will start synthesizing different counterfactual images, because the supervision that's happening or driving this generative architecture is this black box classifier. So essentially, we want to expose or test what is this black box classifier looking at. And finally, if we look at a zoomed in region of this black box classifier, so input is what we explained, a data set which has 6 subjects, with most of the 6 subjects having visual artifact, and healthy subject with no visual artifact, and the other way around. So whenever we have this black box classifier, it's trained with 2 different methods, ERM, which is the usual optimization approach, empirical risk minimization, and the second one being DRO, which is distributional robust optimization. We also have some constraints imposed on these counterfactual images, and these constraints are that the counterfactual image should look like an original subject. So a nice solution to this is that if you want to synthesize a healthy subject corresponding to a sick subject, you can simply copy an image from the healthy subject domain, which we do not want. We want a counterfactual image that belongs to the correct person. Also, we have to check whether it belongs to the correct class, which we call as classifier consistency. And finally, the last one is cycle consistency, which means that we also check the reversibility. So if the generated counterfactual is passed through the reverse generator, it should ideally generate the actual image, which is the input image to either of these generators. Keeping those constraints in mind, here are the evaluation approaches that we use. The first one is identity preservation, as I just explained, that a metric which verifies that it belongs, the counterfactual image is very similar to the actual image. The second one being counterfactual prediction gain, which ensures that the counterfactual image belongs to the correct target class. And finally, the spurious correlation latching score, which identifies which is whether there is a spurious correlation in the counterfactual image or not. So the first 2 are standard metrics that we use, but as I just explained, if we want to evaluate whether the counterfactual image was latching on to the spurious correlation or not, we need something to test whether there is spurious correlation or not, which is proposed by this last score. So in terms of result, we evaluate the performance first of the classifier and second of the counterfactual qualitatively and quantitatively. So here are our results, the classifier evaluation. Dataset 1 is the place where we have synthetic data, where we have artificially induced artifact. Data 2 is a real data set. And the most important point over here is if you look at the performance of the minority class by an ERM-based approach or a DRO-based approach, there is almost a 45% boost in the minority class, which shows that your DRO method is able to generalize better on these smaller subgroups. And in the case of real life example, which is on Checkspert, you still see that there is a small jump in the minority class. And that might be because the spurious correlation might be very difficult to learn, because these medical devices, they can vary in shape, size, position, as well as contrast and occlusion, which is very standard in most of the data set that we see. So a qualitative evaluation for these counterfactual is shown over here. The top image that you see, all the cyan boxes show the position of artifact, and the disease pathology is shown in magenta. The first column that you see over here, these are counterfactuals that are synthesized via ERM approach, the empirical robust minimization. And the second line over here that you see are the counterfactuals synthesized via DRO approach. So essentially, we are trying to expose these 2 methods of optimization that we used. What kind of counterfactuals do they generate? And if you look at the difference map between the real image and the counterfactual image, in the case of ERM, it clearly shows that the only region that you need to change in order to make a sick patient healthy is simply remove the artifact, which is dangerous because now the classification was right for this group. It's a majority group, but for wrong reasons. And if you look at the bottom one, which is the reverse class, so a healthy patient with an artifact, in that case, if you want to make this patient sick, the artifact is simply enlarged. So instead of looking at disease pathology, again, the model focuses on these artifacts. However, in the case of DRO, you see that it's focusing on the region of disease pathology and preserving these artifacts. So the new proposed metric that we have, it is testing whether this artifact is preserved or not, which is not available in the standard metrics that is available out there in the literature. So essentially, the conclusion from these images are ERM, there is no significant change in the region of artifact, whereas ERM shows significant change in the region of artifact, and DRO, there's no change in the region where you have artifact. However, ERM, there is no change in disease pathology, so it ignores disease pathology and latch on to spurious correlation. However, DRO, it changes where you expect the disease pathology to happen. Here are our results, which are also showing the usual standard metrics. So actionability, SSIM, and CPG, which is counterfactual prediction gained, just assuring whether it belongs to the correct target class. It looks distance between the factual and the counterfactual image is minimum. So you see that for both the data set, the ERM and DRO based approach, the performance is similar. However, as I said, that these metrics will not justify our point. So we use this SCLS score, the new proposed metric, and we clearly see that for a DRO based approach, SCLS is preserved, which means that a lower score is better in this case. So the conclusion drawn from this slide is lower SCLS score indicate that this DRO-based classifier does not latch onto spurious correlation. And essentially, as concluding remarks, safe deployment of deep learning models in medical imaging require explainability, because we have had these debiasing architectures, and there are other debiasing approaches as well. But there is a need to expose and mitigate these bias as well as correlations. And we propose the first integrated end-to-end training strategy for generating unbiased counterfactual images, which we believe are useful. And the method that we use over here is a DRO-based classifier, which enhances the generalization over this minority subgroup. So I would like to thank all of you for your attention and listening to me. We would also like to thank our sponsors, which is present over here. If you would like to connect with me, that's my QR code. So feel free to scan.
Thank you very much for the nice talk. Questions? Yes, please. As you like. If you still have energy, you can come here.
Yeah. Yeah. So the question is, when I'm training this cycle GAN approach, the data has already been seen by the model. So wouldn't it be biased, or wouldn't it generate unfair representation of the minority class? I guess that's the. Okay, yeah, so this generative architecture should have trouble generating the minority classes, because these minority classes are underrepresented in the image. That's a very good question, but that wouldn't be the case, because if you look at the supervision of this cycle GAN, most of the gradients is coming from a classifier which has already seen most of the classes. Now, this minority class, which are definitely underrepresented, and that's the whole point of the paper, that you need to debias. If it is not debiased, essentially the representation of minority is very low, and that is what is being shown in this result. So we do not use any other extra data set. We simply change the approach of optimization, and minority classes also get significant representation. And this is being exposed through the generative architecture. So to simplify the answer to your question, if it was an ERM-based approach, yes, the minority representation is low, and hence it will be difficult to synthesize those. But since you are using a debiased classifier, the same kind of problem will not exist in that scenario, and that can also generalize to other methods. So the heart and soul of this this model, you can fit in any black box classifier over there and try to expose that what is this black box classifier looking at. It's not about the representation, whether the input data has a majority or a minority or not, because this domain of sick and domain of healthy, that sick domain contains both majority and minority, and this healthy domain contains both. So all it matters is what sample is are you currently looking at while inference. Any other questions?
I think in the interest of time, we would like to thank you again for a great presentation.
Thank you.
Because actually this was not the end, it's a new beginning, because now we're transitioning over to another exciting part of this joint workshop. Now we're handing over to John Bercea. And don't forget, now you're officially allowed to vote on all the presentations. I will show the code, and while I do this, maybe we can give a round of applause again to all the speakers of the FAIMI.